This next session is entitled The Physics and Gas Laws of Hyperbaric Medicine. Now you may be asking yourself, listen, I want to be a clinician. I want to take care of patients. I don't really care about physics and science and gas laws. Why is this important to the practice of hyperbaric medicine? Well, let's take a look. Here's a hyperbaric chamber. We know there's changes in pressure when we place patients in the chamber. Here is an experiment performed by an inside observer where he fills a bottle with air and then they come to the surface. You can see the changes that happen in these devices. When they exit the chamber, you can see that bottle is very tense and tight. It takes very little effort to open that cap based on the pressure change inside that bottle due to the hyperbaric environment. So, it is very important to understand you're placing patients in a pressurized environment. In a multi-place setting, you may also go in yourself or have attendants inside. You need to understand the implications of these gas laws, the physical aspects and the change in pressure, gas spaces, temperature, and volume to really manage your patients well in a safe and effective manner. So these lectures are going to be delivered by several of the faculty. Dr. Tom Serena will start off taking us through a very detailed overlook and explanation of the gas laws and the physics of hyperbaric medicine. Then in the following session, Dr. Tyler Sexton is going to provide us with clinical correlations. Dr. Sexton is going to walk us through some mathematical calculations that are important to us on a daily basis. He'll look at the gas laws and interpret them through mathematical calculations to give us information that we will utilize for the care of our patients on a daily basis. So, with that being said, physics and gas laws of hyperbaric medicine are incredibly important to your clinical practice. So if you're ready, sit back and relax for a physics and gas law extraordinaire lecture.
Welcome to Physics. This lecture is going to go over the physics of hyperbaric medicine. It's very important. I know you hear the word physics and you're probably shuddering in your shoes right now. A lot of us who are in the biology and liberal arts fields always try to avoid physics. I wouldn't even walk through the building. In any event, we're going to go over some terms and definitions. We'll talk about some units of measure. And then we're going to go over the gas laws and then some additional applicable physical laws and principles that actually are very germane to the practice of hyperbaric medicine. I'm Tom Serena. I've already been introduced, so we'll go ahead and get started on the physics of hyperbaric medicine. This applies to both monoplace chambers and multiplace chambers because they both are pressurized. So pressure, what is pressure? It's a force exerted per unit area of surface by molecules in motion. And there are a number of units. And what I'll do first is we're going to go through some definitions and some terms and go over some units. And you really, most of these units you need to know, not only just for the daily practice, but for test taking in the future. So we use the term an atmosphere. An atmosphere is 14.7 pounds per square inch. It's also 760 millimeters of mercury and then over 100,000 pascals. Now pascals are typically used in our European centers, if you're in the U.S. you may not need to know the pascals, but if you're outside the U.S. We're going to have to know the pascals as well. So pressure is a scalar quantity. It doesn't have magnitude or direction, and pressure acts perpendicular to enclosing surfaces. So, atmospheric pressure. The best way to think of atmospheric pressure is it's the weight of the air on the Earth's surface. And if you look down towards the water there, you see more molecules. So obviously the air is heavier. So this is how we express atmospheric pressure. So it acts on all bodies in the atmosphere. It varies based on weather conditions, and we'll talk about barometric pressure in just a minute. And at sea level, a gauge will measure atmospheric pressure, which would be 14.7 pounds per square inch. absolute atmospheres, 1 atmosphere. Why am I showing a picture of Key Largo Beach? This because Dr. Nizgoda and I held this course, I think last time we were together at this resort in Key Largo. A very nice place to take the course. I hope you're comfortable sitting where you are now. But if you're at sea level, you're at 1 atmosphere. If you're out skiing in Breckenridge, Colorado, that's my son, at the top of the mountain, he's at 8,000 feet. You notice that you have less atmospheric pressure. It's also absolute pressure as well at this point. It's 0.74 atmospheres. If you were able to climb the top of Mount Everest at 29,000 feet, you can see that that would be 0.31 atmospheres absolute. So absolute pressure, it would include atmospheric pressure plus the water. So when we start talking about diving, going underneath the water or a chamber where it's pressurized, we're really going to be talking about absolute pressure. So you have to add atmospheric pressure to the hydrostatic pressure or the weight of the water as well. And we typically measure that in pounds per square inch absolute. Now I mentioned barometric pressure. Barometric pressure varies with the weather, and I stole this map off the Weather Channel, and we're very used to seeing these Doppler radar, and you see these high zones and low zones, and that's variations in barometric pressure or atmospheric pressure. And now, when the weather folks use it, they will use millimeters of mercury as their measurement, and a typical pressure at sea level is 760 millimeters of mercury. That's 1 atmosphere. Now, something I need to explain. Now, this is important if you're an engineer or when you're reading, you need to understand gauge pressure. The other thing you know is for tests, because this makes a great test question. So gauge pressure is what reads on a gauge. Very simple. But it's sea level is its starting point. So it does not include atmospheric pressure. So if we were sitting on the beach in the resort in Key Largo and we had our gauge at sea level, we would be at 1 atmosphere absolute, but the gauge pressure would read 0 because it does not take into account atmospheric pressure. So keep that in mind. And certainly if you're going to go back and take a test at some point, you want to put that in your mind. So if you happen to see PSIG, pounds per square inch gauge, you got to remember does not include atmospheric pressure. So units of pressure, again, absolute pressures, that's ATA is what you're going to hear, pounds per square inch, and millimeters of mercury, just as a review. Hydrostatic pressure I mentioned briefly, but it's the pressure produced by the weight of water on anything that's immersed. So it's a combination of the weight of the liquid and atmospheric pressure. So if we're at 1 atmosphere in Key Largo and we go underneath the water to say 33 feet of seawater, we're now going to be 1 atmosphere underwater, and the total absolute pressure will be 2 atmospheres. If you really want a nice little calculation, hydrostatic pressure increases 0.445 pounds per square inch per feet of seawater, and it's fresh water is less dense, so you'll have only 0.433 in fresh water. And you may see this on a test, so I'm going to go over it real quickly. I believe that if you do, they will give you those conversions, and it's really pretty simple math. 100 feet of seawater, how many pounds per square inch would that be? You take 150, you multiply by the conversion factor, 0.445, and you come up with 66.75. Similarly, 90 feet of seawater, you multiply by the conversion factor, and you get roughly 40 pounds per square inch. And then freshwater, and this is where you might see this on a test or something. Maybe you're taking your CHT exam, and they just want to make sure that you really understand the concept. So they put in feet of freshwater. Now the conversion factor is different. This would be 0.433. And again, I don't think you need to memorize these conversion factors. In most tests, they are provided, but you need to understand how to convert from one to the other. feet of seawater, 10 feet of seawater is about 1.3 atmospheres, or 19.5 pounds per square inch. And 33 feet is 2 atmospheres, 66 feet, 3 atmospheres. So remember, when you're doing your calculations, it's almost always done in absolute pressure. And when we talk about hyperbaric, and we do hyperbaric, we're really going to be talking about ATA all the time. And that's what you can hear over and over again. The other thing that if you're a tech, you're going to hear a lot of is the pounds per square inch. Another concept or definition we need to introduce is partial pressure. That's the pressure exerted by a given gas in a mixture. Partial pressure is directly proportional to the gas percentage of the total volume. We're going to talk about this a little bit later when we talk more about partial pressure. But that is an important concept. And it's going to be very important in divers who are going to be absorbing nitrogen. Partial pressure is going to be very important. It's also important in our hyperbaric patients because they'll be absorbing oxygen, and that'll be dissolving into the plasma. So now, let's go on to the gas laws. The ideal gas laws, you may remember this from your high school or college days, we used to call this PERV-NERT, is really made up of 3 separate gas laws. And we're going to go over the first gas law, which is really the most germane to our topic. This church doesn't have anything to do at all with the gas laws, except that this church is outside the Pale in Dublin. Outside the Pale means outside the area that was controlled by England, and it was thought to be a fairly lawless area. So if you're going to take a ghost tour in Ireland, they take you to a church outside the Pale, and there's all kinds of really interesting ghost tours if you get a chance to do it. But in any event, why is that important? Because when I was taking the ghost tour, I saw a grave inside the church, or a monument inside the church, and in that monument is Sir Robert Boyle, who our gas laws are named after. Turns out his mother is buried in that church. So this is Sir Robert Boyle. And Boyle's law is that at constant temperature, the pressure and volume of a gas are inversely proportional to each other. I'm going to repeat that. At a constant temperature, the pressure and volume of a gas are inversely proportional to each other. So if pressure goes up, volume goes down, volume goes up, pressure goes down. It's the only inverse gas law. So this is the one, and this is the one you really have to have a handle on. So if you look at this diagrammatically, I showed the slide from NASA, you can see that you get, as you increase pressure, you decrease volume. So here's a nice example. A diver inflates a balloon with 100 cc's of air at 33 feet of seawater. So what will the volume be when he reaches the surface? Now, it's an easy calculation. The pressure 1, volume 1 sum is, combination is equal to P2 V2. And we do that math. You see that the balloon actually has 200 cc's when he gets to the surface of air. And that's because as you go up, pressure decreases, volume therefore increases. So if you look at it, and you look at bubbles, or balloons in this case, you see at the surface you have a balloon size, and as you go deeper, you get the bubble or balloon will get smaller and smaller. And it's really important. One thing I want to draw your attention to is that first drop in 10 meters, so to 2 atmospheres. Look at the size of that balloon. It really decreases by 50%. Now that is where there's the greatest change in volume as you're increasing pressure. It's that early. So what does that mean to scuba divers? If you've ever gone scuba diving, you know that the instructor always tries to get you to clear your ears in that first 10 feet. In addition, this is when you're diving patients, this is when they're going to have their ear trouble. During the descent, as they're going down, the airspace is now getting smaller. And it's doing, and that greatest change is going to be in that first part of the dive. So this is when you want to be at the chambers, a new diver, or a new patient and saying, okay, clear your ears, do the things you need to do to get the eustachian tubes open and free up that air space. So again, I'm repeating myself, and for a reason. Boyle's law is the only inverse relationship. You can, styrofoam cups are mostly just air, so you can actually put them in a multi-place chamber and watch them get smaller and smaller. So what relevance does Boyle's law have to hyperbaric medicine? Well, during descent, which is the compression, that's where we're going down, the patient's going down, the diver's descending in the water, that's when your pressure is going to increase and your volume is going to decrease. And that has a lot of effect on air-filled spaces like your ears. So patients may feel ear squeezed. If they have a cold, I have allergies today, you can probably hear it, then the sinuses may squeeze as well. So anything that has air in it is going to be an issue. And that's the way you need to think about safety in hyperbaric when you're talking about the gas laws. Does this space have air in it? Does it, if it does, it's something I'm going to have to worry about or be concerned about. So the other area that's important is now when the patient comes up. So they're at the bottom, so as they come up, they are going to have, their pressure is going to decrease, volume is going to increase. So if you had a patient with a pneumothorax, for example, that was untreated, that potential space in the thoracic cavity is now going to increase, and it could cause a tension pneumothorax. That's why pneumothorax is one of the contraindications to having patients dive. So Boyle's law, very important to hyperbaric medicine, very important to your patients, and if you're a diver, very important to you in that regard as well. Think about air-filled spaces and the effects that pressure will have on them. It's the only inverse relationship. All right, let's go on now to Charles. Charles' law, actually Charles did not describe Charles' law, but he was a famous scientist, mathematician, balloonist, and he obviously discovered that if you put hot air in a balloon, you can expand it and it will go up. This is a direct relationship. As temperature increases, volume increases. As temperature decreases, volume decreases. Now you notice I didn't mention pressure. So as we go through all these subsets of the gas laws, one of the parameters has to stay constant. So in this case, in Charles' law, pressure stays constant. And temperature may increase or decrease, and that's a direct relationship. So unlike Boyle's law, which was an inverse, this is a direct relationship. Temperature decreases, volume decreases, temperature increases, volume increases. And that's shown in this relationship. Again, I don't think you need to know the math here, but in case you like to do math, you know, if you do, if you had an example like this at 200 Kelvin, now if you're calculating Charles' law, you have to use Kelvin as the temperature measurement. If the volume of the gas is 100 cc's, the temperature is raised to 300. What will the new volume be? And you can simply solve that. You know what? I'm going to let you solve this. This is one you can do in your head. And if you can't figure it out, let me know. All right. The next law, the third of our gas laws, is Gay-Lussac, and this time we're going to leave volume the same or constant, and what we're going to do is we're going to increase temperature and the pressure increases. We decrease pressure, temperature decreases. And this is just shown diagrammatically, and if you think about this one, it's really how fast are the molecules moving. So clinical relevance for this is that it's one of the reasons that we don't leave scuba tanks in the sun. We used to say they explode. They don't actually explode. What happens is that they have a vent on them. So if you leave a scuba tank in the sun and you increase the temperature, then you'll increase the pressure. So what will happen to the air in the scuba tank is that it will vent out. So when you go to do your dive and you want to go see all the great fish, you realize that you have no air. It's a bad thing when you're underwater. So that's really the relevance. It's also why the patient may feel warm during chamber compression, and they may feel cool during chamber decompression. You know, to be very honest, we don't really notice this in a monoplace setting, in most clinical settings, because the patients are being having a descent and ascent that's relatively slow and not as deep. But if you're doing multi-place work and you're doing particularly research on younger individuals, and we've done this, and you're going down rather rapidly to deeper atmospheres, say 4 or 5 atmospheres, and you do it in a rapid fashion, you can see them sweating in the chamber. It does get quite warm. But in most clinical situations, you won't find this to be a very applicable law. Still need to know about it. So we put them all together. So in this diagram, you can see that Boyle's law is the inverse relationship between pressure and volume. Charles' law is the direct relationship between volume and temperature, and Gay-Lussac is pressure and the direct relationship between pressure and temperature. Now we have some more folks to talk about. Dalton. Now, Dalton was a super scientist, developed the atomic theory of matter, devised a system of chemical symbols, actually devised a system to tell if you're colorblind. Did a whole lot of things, but he also did something that is applicable to hyperbaric directly, and that is that he said he has the Dalton's law, which says that the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures. And it's the partial pressures that do the work. And it's the partial pressure that has the clinical effects of the gas. And that's just shown diagrammatically. In practical terms, again, I've already mentioned this, but in practical terms, the partial pressure is responsible for the physiological effects of the individual gas. And then it's typically presented in percentages, and they define the ratio between the number of molecules in a mixture. So you do need to know this. Again, physics has both a clinical and very practical knowledge point, but it also, at the same time, we always are concerned about test taking. All right, next law, Henry's law is another one that's very applicable to hyperbaric medicine, and it's why soda fizzes. Although I'm here in Milwaukee now, I really should have shown probably Miller, a Miller beer here instead of Coke. So here we go. This is Miller Lite. Henry's law says that the pressure of a gas at the interface with a liquid. So you have a gas touching a liquid, determines how much of that gas gets dissolved in the liquid. So look at the screen here where we have the cap. So you see the cap is on, and we have high pressure. That's how we make it. So if there's high pressure, then the gas that's in contact with the liquid has a very high pressure. So that means that a lot of that gas is now dissolved in the liquid. When you remove the cap, decrease the pressure, you decrease the partial pressure of the gas at the interface, and what happens? You get foam in your beer. You get effervescence, and you get gas bubbling because the gas is coming out of the liquid. And this is Henry's law, very applicable to how gases get into the bloodstream. All right. So here it's just shown diagrammatically for your own sake. The volume of gas dissolved in a liquid directly proportional to the partial pressure of the gas in contact at the interface with that liquid. So it is really relevant. The greater the pressure, the more the gas dissolved in a liquid. It explains why, if you're diving underwater, that the divers will take up large amounts of nitrogen. They're breathing air. Air is 80%, roughly 80% nitrogen. So they're taking a lot of nitrogen because at the alveolar interface with the blood, a lot of that nitrogen is dissolving into the blood, and that's why it's important for decompression illness and for bending tenders. It's also very important for how hyperbaric works. One of the ways that hyperbaric works is you dissolve lots of oxygen into the blood. And how are you going to do that? Well, if you increase the partial pressure of oxygen inside the lungs, where the alveoli meets the pulmonary capillaries, then you're going to dissolve a lot of oxygen in the blood, but as you increase the pressure, because the partial pressure of oxygen will go up. So this explains why divers can have difficulty with nitrogen. It also explains why hyperbaric works. Another important equation is Laplace's equation, and you can read this. This is probably the limit of my physics ability, but this is included in your slides, and it describes basically there's two pressures on a bubble. There is the surface tension, and then there's the outward pressure of the bubble itself. What you need to understand is that the smaller you make the bubble, the more likely it is that it will dissolve. So if I'm a diver and I get nitrogen bubbles in my blood because I've bent myself, then I put the patient in a hyperbaric environment. I increase the pressure. So what happens to a bubble if I increase the pressure? The volume decreases. By Laplace's law, the bubble then dissolves into solution, and hence the treatment for decompression sickness. There's a lot of very complex mathematics. One afternoon I thought for fun I would try to figure it out. Good luck. All right, next is Blaise Pascal. And he's important in that the pressure exerted at any point on a confined liquid is transmitted equally throughout. So earlier on I said you only need to worry about spaces that have air. That's Blaise took care of the liquid and solid spaces for us because, again, the pressure is distributed equally throughout, so we don't have to worry about, we really don't have to worry about liquids. So it's why if you're, for example, if you're in a hyperbaric chamber, your blood pressure shouldn't change because the pressure should have no effect on the blood pressure. Actually, there are other mechanisms going on, so the blood pressure probably does change, but at least as it's applicable to Pascal's law, because the pressure is distributed equally throughout the liquid, really no changes in things that have the spaces that contain liquids. All right, let's go over the gas laws again, just in summary. Boyle's law. At a constant temperature, the pressure and volume of gas inversely related. Pressure goes up, volume goes down. Probably the most applicable law. You need to know this more than just for test taking. In a minute, I'll give you some examples of how we've used Boyle's law in practical applications. Charles' law, at constant pressure, the volume of a gas is directly proportional to the temperature. So temperature increases, volume increases. Gay-Lussac, at a constant volume, this time we're holding volume, as temperature increases, pressure increases. This is the scuba tank example. Dalton's law is that the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of each of the different gases made up in the mixture. So it's why if you're, for divers, and you're breathing air, which is 80%, roughly 80% nitrogen, the nitrogen percentage is going to be very important. Henry's law is that the volume of a gas dissolved in a liquid is directly proportional to the partial pressure of the gas in contact with the liquid. So, in the world of beer, very important because we want to have a nice, bubbly, gaseous beer. And in the world of hyperbarics, we want to increase the amount of oxygen dissolved in the patient's blood. And we want to be concerned about tenders in a multiplace chamber or divers who are going to get nitrogen dissolved in their blood. We certainly don't want that to form bubbles. Laplace's equation is the surface tension of a sphere decreases as the radius increases. In other words, you make the bubbles smaller, you're doing a good thing. You're going to have them dissolve into the liquid. And Pascal's law was that pressure exerted at any point on a confined liquid is simply transmitted equally throughout. So, all right, now we're going to do some clinical examples. And I'm really going to try to show you how, in some examples, we've actually applied Boyle's law, mostly Boyle's law, to practical everyday matters. So the first case was a case that probably couldn't occur today, but it was just a while ago. I'm old. So the patient had their air brake hose going in through the chamber, and it has a one-way valve on it right where the mask is. And it had been the tubing had been hooked up incorrectly. And when they turned on when the CHT turned on the air, the tubing got a bubble in it. And I got a frantic call because the patient's now at 2.4 atmospheres, and there's this bubble in the tubing, and what do you do? Now remember, you're thinking about the gas laws. The last thing in the world you want to do is start your ascent, because now the bubble will get larger. Okay, again, as you decrease the pressure, that bubble in that tubing is going to expand. Really nice little experiment. Like I said, today we have safety measures in place that can't really happen anymore. But it's a good example, and it's a real one. So I was thinking, okay, what can we do? Well, you could always bring the patient, bring him up anyway. There's nothing flammable about a tube exploding, but you hate to have tubes exploding, in the chamber. That's not a good thing. Obviously, the practical answer, if you're thinking about this, is you simply have the patient take the mask off and open up the valve, and it decompressed. But an interesting example of why you might have to know that. Here's a more practical example, and a true one. So we had an elderly woman who had a diabetic foot ulceration. I believe she was in her early 90s, was receiving hyperbaric treatment, doing very well. And it was on Sunday evening. She went to go to the bathroom late in the evening and fell and struck her chest on the side of her bathtub. She went to the emergency room at not our hospital, an outside hospital. And they took an X-ray, looked fine. She comes in the next day for hyperbaric treatment and actually never mentioned the fall, never mentioned the trip to the emergency room, even after, despite that we do a brief review of systems. Hey, has anything changed? How'd the weekend go? But she just, she was 92. She just didn't remember it, and or think to report it to the tech or the doc. Anyway, in any event, she gets to the chamber. She's now pressurized. She was diving at 2 atmospheres, and we get a frantic call from the emergency room at the other hospital saying the patient has a pneumothorax. We missed the pneumothorax on the chest X-ray. The radiologist came in this morning, is reviewing it. We know this patient is a patient of yours. You're treating with hyperbaric, and now what do? You have someone at 2 atmospheres with a pneumothorax. And it wasn't a large one, just a couple centimeters, but now you're facing a real problem. The patient's at depth. You've got to bring them up, and they have there's a potential that pneumothorax will get much larger as the pressure decreases. The volume of the pneumothorax is potentially going to get bigger, and it could even cause a tension pneumothorax. So what do you do? Again, another true case. I happened to be in attendance during this one. It was very interesting. So what we did was, well, I wish you could tell me what we did. But in any event, the first thing you do is get your chest tube tray ready, or your needle, so that you can decompress it in case there is a tension. You want to be able to do that right away. And then we brought the patient up very slowly, giving the gas more time to equilibrate. And it actually brought her up over about 20 minutes. She did just fine, and actually, in actuality, had no problems. We actually followed her with serial scans to see, to ensure the pneumothorax was resolved. Then she went back in and completed her hyperbaric treatment. Another practical example of understanding the gas laws. Again, they are important, and they are practical. And when we get into the complications section, I may even give you more practical examples of how to use Boyle in day-to-day life. All right, I hope you were able to make it through the physics lecture fairly well, and are looking forward to some more of the clinical presentations. Thank you very much.
Now let's talk about hydrostatic pressure. Hydrostatic pressure is created by the weight of water. All right, this pressure is cumulative, meaning it's additive. The deeper the dive, the more water that's above the diver, therefore the greater amount of pressure is exerted on the diver. Now, hydrostatic pressure is equalized around that diver equally. That's why we don't look like a tube of toothpaste when pressure is exerted on us. All right? The most important form of this pressure is hydrostatic pressure. All right? It increases at a rate of 1 atmosphere every 33 feet of seawater, or 10 meters. But for our case, like I said, let's focus on 33 feet of seawater. So, absolute pressure is denoted by a big ATA. So throughout this course, you're going to hear me say big ATA and small ATA. Small ATA is gauge pressure or hydrostatic pressure, but big ATA is absolute pressure. Okay? Now here we go. Absolute pressure is atmospheric pressure plus the hydrostatic pressure. Now, atmospheric pressure is usually going to be equal to 1. When you're at sea level, it's 1. Now, yes, if you go up to higher altitudes, say mountain regions, those kind of things, or up in a plane, you have a decrease in your atmospheric pressure. Could be 0.5, could be 0.67. But for this course and for what's necessary for exams that you will take in the future, let's just focus on the fact that atmospheric pressure is equal to 1 for this. Okay? All right. Pressure, as I said, was force over area. Now this slide offers you a little bit of a cheat sheet and denotions of how to label pressure. So we use 33 feet of seawater. It can also be denoted as 760 millimeters of mercury, 101.3 kilopascals, and 14.7 pounds per square inch. So we're going to talk about how to convert between these types of measurements, because some of our chambers will be in millimeters of mercury, some of our chamber gauges may be in feet of seawater, and some of them may be in PSI. I'm going to teach you how to calculate between those so that you, as a hyperbaric tech or the medical director, will know exactly what depth your patients are being treated at. Now remember, as a physician, we usually speak in absolutes. So if I told my patient, my tender, to take my patient down to 2.4 absolute, or 2.4 atmospheres, let's say, I am actually speaking in absolutes. 2.4 absolute atmospheres is very different than 2.4 gauge atmospheres. As a matter of fact, it's an additive 33 feet. So if my tech didn't know the differentiation between 2.4 absolute atmospheres and 2.4 gauge pressure atmospheres, you would be at risk of developing, say, a central nervous system toxicity in the form of a seizure, for example. So that's why this is important to go over. All right, now again, absolute pressure. One of the things I wanted to let you know is that 1 absolute pressure is equal to 33 feet of seawater. So here is your cheat sheet for now, and we're going to go through this. At 0 feet of seawater, or at sea level, right now where we're at, we are at 1 absolute atmosphere, or 1 big ATA. At 33 feet of seawater, it is at 2 absolute ATA. At 66 feet, 3. So if I told my chamber operator to take my patient down to 2 absolute atmospheres, that is drastically different than asking them to take them down to 2 atmospheres gauge. As you can see from this, 2 absolute atmospheres is 33 feet of seawater. Okay? Whereas 2 atmospheres gauge would be 66 feet of seawater, and you'll see this. Whereas 3 absolute atmospheres is 66 feet of seawater. Okay? All right, something I want to show you as we continue to follow and calculate some things. There's a quick little graph that I learned that made it easy for me. When we are calculating, and we are using a variety of different conversion factors, as you're going to see, if I give you millimeters of mercury, small ATA, PSI, in order to get to absolute atmospheres, which is up here, big ATA, you're actually jumping up the stairs, or stepping up the stairs, meaning you're going to add 1. That means if you start with any of the 3 that you see below, Once you've figured these answers and you want to get to absolute atmospheres, you want to convert to this and then add 1. If you are here in terms of absolute atmospheres and you want to get to one of these below, you will actually subtract 1, and then that will equalize and allow you to do that. This will become clearer, but I just wanted to make sure this got noted to you. All right, gauge pressure is the absolute pressure being measured minus the pressure being measured inside the tank, or a gauge pressure. What does that mean? That means that if I brought a scuba diving tank in here with us and I put a regulator on it, what is it normally going to read? It's going to read 3,000 psi, usually. What does that mean? That means there's 3,000 pounds per square inch inside that cylinder. But what it doesn't give us is that there's also an added ambient or absolute atmospheric pressure that is outside. So yes, while the gauge is reading 3,000 pounds per square inch, which is correct, that's the gauge pressure, there is also the outside absolute pressure. And as we know, one absolute atmosphere equals 14.7 psi. So 3,000 pounds per square inch inside that cylinder is correct, but the total pressure that that cylinder is actually exerted under is 3,014.7 psi, because you're adding to account for absolute pressure. All right, so I'm going to talk about density really fast. Density is the weight over the volume. All right, and density is important to know because density is directly proportional to pressure. And this is interesting because as you increase the pressure, volume decreases, right? Or the molecules get closer together. Now the volume of a gas will get smaller based on Boyle's law, which we're going to talk about. But at that same time, you are compressing those molecules closer together, and they have closer to vibrate, and they get hot. But that packing them in closer together thus makes it very much more dense. That's why the deeper you are, the harder it is to breathe. Say you were doing a treatment at 45 feet of seawater and 165 feet of seawater. That air will feel more dense, or it takes you a little bit more effort to breathe. That's also why a scuba diving regulator has what's called a demand component, where it will actually force air into your lungs at deeper depths because it has to overcompensate the amount of pressure, or the fact that that gas is now denser because it's being compressed by the water around us. Let us go ahead and do a couple practice problems about how to convert to different pressures. I think that's more easily demonstrated if I show you a few. It becomes a lot more clear. So let's do a couple together. So first, let's say I am at 60 feet of seawater. What is that in absolute atmospheres? Well, let's find out, all right? So how do we do this? First, we go ahead and do 60 feet of seawater divided by our 33 feet of seawater, which gives us 1.8. And that is denoted as a small atmosphere. All right? Now you've seen this equation before. Now to get from a small atmosphere to a big atmosphere, or absolute atmospheres, you must add 1. So 1.8 plus 1 is equal to 2.8. So 60 feet of seawater is synonymous with 2.8 atmospheres. Let's do another one together. Let's say we go ahead and say, what is 33 feet of seawater in absolute atmospheres? Well, that one is 33 feet of seawater divided by 33. That equals 1, small ATA. You add 1, and that gives you 2, big ATA. All right? Let's go ahead and take a couple other examples as we go along. Alright, so now we know how to do the basics that you see on your table. Now I can do a variety of different things. I'm going to do a few more examples with you, and then I'm going to add in millimeters of mercury and things like this. You need to be able to synonymously be able to change between these types of equations or problems, because you will see this on any test that you take in hyperbaric medicine. Let's continue a few more examples. Our next one is, let's say we have 6 ATA, and we want to know how much that is in feet of seawater. Well, now we're just going to go the other direction. Alright, so we do 6 ATA minus 1 to get to small ATA, which equals 5. Now we have 5 small ATA, and we want to know what is that in feet of seawater. Well, we know that 1 ATA is equal to 33 feet of seawater. So you simply multiply 5 times 33, which will give us 165 feet of seawater. Let's do another one again. Let's say I want to know what 4 big ATA is in feet of seawater. Alright? Well, coming up, how do we figure that out? It's very simple. We take 4 minus 1, which gives us 3 small ATA. To get to feet of seawater, we take that 3, we multiply it by our conversion factor of 33 feet of seawater, and that gives us 99 feet of seawater. You now easily know how to calculate between feet of seawater and atmospheres, for example. Now let's look at doing it between millimeters of mercury, psi, or atmospheres. We're going to do a couple together. Now, before we cut over, I want to tell you I have given you lots of equations to practice at home, and I would strongly encourage you to do this, as this is the basic foundation and building blocks of hyperbaric medicine and why we do what we do. For those of us out there who have been doing this for a long time, this would make sense. But I wanted to make sure that we covered the basics in terms of calculations to make sure you're well prepared and that you are well equipped to handle any calculation. Let's continue. Let's say we are doing a question of trying to convert 6 ATA absolute to pounds per square inch. Now this one's pretty easy. Since we've got the absolute atmospheres, all we have to do is first get to atmospheres. 1 atmosphere is small. Remember, and I want you to remember this really fast, 1 atmosphere, and write this down, 1 atmosphere is equal to 33 feet of seawater, which is equal to 14.7 psi, which is also equal to 760 millimeters of mercury. Alright? So this is very important that you see all this. This is your basic conversion that you're going to use for everything else. Looking at 6 ATA into pounds per square inch. First, we subtract 6 minus 1, which gives us 5 small ATA. Now to convert to PSI at this point, we simply take 5 times 14.7, which will give us 73.5 PSI. Alright? Let's do another one. Let's say I want to get to millimeters of mercury now. I am looking at, let's say, 4 absolute atmospheres. And what is that in millimeters of mercury? Well, first what we do, we must always get to small ATA. We know how to do that. We take 4 minus 1, which gives us 3 small ATA. Now, from there, it's a very simple calculation in which we take 760 millimeters of mercury and we multiply that by 3 small ATA. And that will give us 2,280 millimeters of mercury. I would encourage you very much to continue to practice these. As I continue in this lecture, we're going to build on the things that we've already learned when we start applying the T-score, which you'll see in later slides. Okay? But we're going to do a couple more together as this lecture goes on. All right, now we've been talking about partial pressures of gases, and you now know what Dalton's law means. But I'm going to show you something called the T formula. This formula is critically important because with this you can calculate the partial pressure of any gas at any depth. So let's do a few of these together. All right, we know that our T formula is the partial pressure of a gas is equal to the fraction of that gas that we're looking at times the atmosphere. So let's say I want to know what the partial pressure of oxygen is when I am breathing 50% oxygen at 6 atmospheres. Well, this is easy to plug in. We plug and play. All right? So we go ahead and do this. We know what our atmosphere is. We are looking for the PO2. We know that I was asking you 6 ATA, that was the depth we were at. And our fraction of a gas is 0.50. You convert every percentage into a fraction at this point. That means the PO2 is equal to 3 ATA. That means the PO2 is equal to 3 ATA. Let's do another one together. Let's say I want to know what the partial pressure of a gas is. Breathing at 99 feet of seawater, breathing 32% oxygen mix, or nitrox, which you will learn further about in this course. What is the PO2? Well, how do we do that? It's a couple steps. First, we must calculate the feet of seawater into atmospheres first. Well, we know how to do that. We take 99, divide that by 33, which gives us 3, plus 1, which gives us 4 absolute atmospheres. Right? Because this is equal to small ATA. So now we know that part of the equation. We also know that we're looking for the PO2 in this question. We don't know what the FO2 is, but we know what the depth is, and it has to be converted to big ATA. So now we just solve for the equation. We know, based on what I gave you, that we are breathing a 32% nitrox mix. So therefore we can replace this X with 32. So now all we're doing is solving the equation. PO2 is equal to 0.32 times 4. And that gives us an answer of 1.28 atmospheres. Let's do one or two more together and then we'll be done. Let us say that I am breathing 100% oxygen at a depth of 14.7 psi. All right, what's my PO2? We know what the fraction of a gas is at that time. We're looking for PO2. We know we're breathing 100% oxygen, so that makes our fraction of a gas being 1 or 100%. And we must calculate what that atmosphere pressure is, absolute. So that's 14.7 psi is equal to 1 ATA. So to get to big ATA, we merely add 1, which equals 2, which means that the PO2 is equal to 2.0. Now, temperature conversions, we're not going to do a lot of these. I do encourage you to practice this, but I want to give you one equation that makes all this very easy. This is written down for you, but basically, let me show you an equation that I use. Fahrenheit is equal to 1.8 C plus 32. So by using this equation, you can also isolate Celsius as your variable in which you need to solve for. So by moving these variables around, you can see that F, or the Fahrenheit, minus 32 divided by 1.8 will give you Celsius. These two equations are basically what I've given you in writing on the last slides. Make sure you commit this either to memory or on paper. And then, with any equation or any problem that I give you, by using these, you can come up with the answers. Alright, now let's just do a couple practice questions together. I'm not going to do that many, but I did want to make sure that you and I do them together so you have something that you can reference back. I'm going to give you a type of question, and basically if you follow the way that I'm doing this for every question, I'm going to do about 5 different questions for you. And if you follow our procedures, you will be able to answer any question by yourself. So let's go ahead and begin. First, let's go ahead and do a couple practice questions in converting atmospheric pressure. Let's say first that we have 1520 millimeters of mercury, and we want to convert this to absolute atmospheres. Well, how do we go ahead and do that? Well, let me show you. Let's go ahead and divide 1520 by 760. That's going to go ahead and give us an answer of 2 ATA. Now this is your gauge pressure. Now to move to absolute, you merely add 1, and that will give us a 3 absolute atmospheric pressure. Alright? For our next one, let's go ahead and convert 132 feet of seawater into PSI and absolute atmospheres. Alright, so let's go ahead and do that one together. First of all, we go ahead and do 132 feet of seawater, divide that by 33, and that will give us 4 small ATA. Now to get to PSI at this particular point, what do? Remember that 1 ATA is equal to 33 feet of seawater and 14.7 PSI. So we take 4 and we multiply it by 14.7, which will give us 58.8 PSI. Now, to go ahead and convert that from 4 small ATA to big ATA, or absolute ATA, we merely add 1, which will give us 5 ATA. So, in recap, 132 feet of seawater is equal to 58.8 PSI and or 5 absolute atmospheres. Alright? Next up, we're going to do a couple questions in regards to calculating partial pressure of a gas. Now remember, our T formula is the partial pressure of a gas is equal to the fraction of said gas at whatever atmospheres that we are at, or whatever depth we are at. Alright? So let's go ahead and do that together. Let's say I want to dive at 66 feet of seawater, and I'm utilizing 32% nitrox. What's my PO2? Let's go ahead and do that together. First, we go ahead and we calculate for the feet of seawater and turn it into absolute atmospheres. We divide this by 33, which gives us a total of 2 ATA. Add the 1, gives us 3 absolute atmospheres. And therefore we continue with the equation that we know, which PO2 equals the fraction of the gas times 3 absolute atmospheres, because we calculated that from the 66 feet. We know what the fraction of the gas we're using is. We're using a 32% nitrox mix, which means that our fraction of a gas in terms of oxygen is 32%. Now remember, that means we're going to plug this in to here, to the fraction of a gas. And so our equation looks like this. That gives us a total of PO2 equaling 0.96. Now I want to tell you guys something. Now make a note. I could ask you at any point to solve for not just PO2, but PN2, or the partial pressure of nitrogen. Now at this point this is very different, so let's do one. It's the same, but I just want to make sure you've seen it. So let's say I want to breathe. Let's say I want to use 36% nitrox at 50 feet of seawater. What is my partial pressure of nitrogen? All right, well, how do we do this one? Well, let's do it together. All right, so we're looking for the PN2. Well, we know our formula, in terms of the T formula, is PN2 is equal to the fraction of the gas that we're breathing times atmospheres. Well, I can easily calculate the atmospheres by doing 50 divided by 33 plus 1, which comes out to be 2.5 ATA, right? Well, now we also know, we know what my ATA is, and that's 2.5 up here to complete it. But we know that I'm breathing a 32% nitrox mix. Now remember that nitrox is demarcated by the first number being oxygen. Well, I didn't ask you for the PO2, I asked you for the PN2. So how do we figure that out? Well, very simply, we take 100 because of Dalton's law, we subtract 32 because that's our fraction of oxygen, which then leaves us with the fraction of nitrogen, because nitrox is a mix of nitrogen and oxygen. That leaves us with 68% nitrogen. Now, that being said, we know now what to do. We know that a PN2 is equal to the 0.68 that we breathe times 2.5 ATA. That then becomes a very simple equation and a simple mathematic problem that we can do together, and the answer comes out to being 1.7 ATA as being your partial pressure of nitrogen. Alright guys, now that completes our review of physics. I hope you guys have learned something. I know it's a lot. I know it feels a little bit overwhelming perhaps with all these math problems. Please practice these at your own leisure, and I promise you that you will see these again on some sort of exam that you take in hyperbaric medicine.